All right, the next lecture is going to be looking at calculating the enthalpy of a reaction, specifically one that occurs in an aqueous medium. So when we mix two solutions into a calorimeter, like the picture I've just drawn here, a typical calorimeter will be a couple of coffee cups in which one sits in the other one, creating a cover. You mix the two solutions together, immediately close it, and then you have a thermometer that sticks through the top of the cover. This system is considered a closed system, therefore heat or energy doesn't leave the system or come into the system. That's the assumption. You do get to have a little bit of heat loss, but on almost all the national exam questions, they'll say treat it as negligible. Now, in that chemical reaction, because they're aqueous solutions, particles A and B can move around, and when they do collide with each other, if they do successfully react, they can either produce energy, which is then going to go out into the solution and heat it up, or they're going to require energy for the collision to reach product state, and therefore they will pull in additional energy from the solution. In either way, the solution, the water, is going to change temperature. So one of the key things you must remember is that the calorimeter is going to only be able to measure the surroundings. So what your thermometer is measuring is typically the water. And if the temperature of the surroundings, the change in temperature of the water is going up, that tells me that the water, the surroundings, is absorbing energy. And it's absorbing energy because the chemical reaction has released it. And therefore, the Q of the reaction, the heat of the reaction, is going to be equal the surroundings, but opposite in sign. It's equal and opposite. And that's because, again, the surroundings, whatever it absorbs, is because the reaction released it, and releasing of energy is a negative value because it's exothermic. So a key thing in this unit you must understand is whenever you have a reaction occurs in an aqueous solution, the calorimeter is going to measure the surroundings. If they ask for the heat of the reaction, you have to know that you just got to simply flip the sign of the value that you give the solution because the reaction is equal and opposite. Okay? Once you know the Q value using MC delta T, to calculate enthalpy is pretty simple. You just take that Q value and you divide it by moles. And specifically, you divide it by not the total moles, but you divide it by the moles of one of the reactants or products. And usually they're going to specify which reactant or product they want the chemical reaction enthalpy to be in. So if they say, what is the enthalpy of the reaction per mole of aluminum, in like that last problem we had last week, you want to make sure that you are dividing the heat of the reaction by the number of moles of aluminum that you have. And when you divide that, you're going to get the heat per 1 mole of aluminum. Okay? So they'll usually specify which reactant or product to divide the moles by. A common mistake is students want to divide the heat by the total summation of all the moles in the reaction. That is incorrect. We only want to divide by a specific reactant or product that is identified. And if they don't identify it, then just pick one and say this is the enthalpy of the reaction per mole of this. All right, so let's go ahead and do a mathematical problem. So you can read here the problem. A student mixes 50 milliliters each of 1 molar hydrochloric acid and sodium hydroxide. The temperature of the resultant solution increases from 21.1 to 27.5. Again, this temperature change, this is going to be the surroundings, the water. Okay, the solution is the water. Calculate the enthalpy change of the reaction in kilojoules per mole of HCl. So they want this per mole of HCl, assuming that the calorimeter loses only negligible quantity of heat. So only a small amount of heat is lost, and we're going to consider it negligible. So in essence, 0. The total volume of the solution is 100 milliliters. The density of the solution is 1, and the specific heat of the solution is 4.18. This is very common. Typically, the enthalpy of the reaction is going to be equal to water if it's a water-based reaction, And that's typically because water has such a higher specific heat than any of the other solute particles. However, not only does the water heat up, but also the particulates of A and B also heat up. But we make a big assumption here. We assume that A and B have the same specific heat as the water. Now, is that correct? No, but it's an assumption we make just to keep the calculations easy, but that does cause some error to pop into the overall problem. Okay? All right, so to calculate the Q of the solution, again, the solution is the surroundings. It's going to be MC delta T. All right, now, they tell us that the solution has a volume, a total volume of 100 milliliters. However, we cannot plug volume in for mass, and this is why they gave us the density of it. The density is 1. Mass is equal to density times volume. So 1 gram per milliliter times 100 milliliters equals 100 grams precisely. Now, typically the density is not 1. It's going to be something other than 1. So usually if you do have solutions and they don't give you the mass of the solution, you might have to make use of the density equation to figure out the mass. All right, so the mass is 100 grams. The specific heat is 4.18 joules per gram Kelvin. Now we are in Celsius. A degree change in Celsius is the same as Kelvin, so I can quickly flip-flop the Celsius. And then the change in temperature is always final minus initial. Now, it increases from 21 to 27. So since it increases from 21, I know that the 27.5, based on that verbiage, is the final, and 21.1 is the initial. All right, so I'm going to pull my calculator, type this in, and multiply it out. And I'll round the final answer to 3 significant figures. And the Q of the solution is 2,680 joules. Okay? So the solution has got a positive value. So that tells me the solution absorbed energy. This is why the temperature of the water-based solution went up. So what does it tell me about the reaction? Well, remember, the reaction is equal but opposite the surroundings, the solution. So the reaction is negative 2680 joules, or negative 2,680 joules, because the reaction released 2,680 joules of energy to the surroundings. So it's negative because this reaction is exothermic. Whenever you have an exothermic reaction, the surroundings are going to be heated up by that release of energy. All right, lastly, since now I know the Q of the solution, to calculate the enthalpy, I just simply take the heat of the reaction and divide it by the moles. Now, a couple things. First of all, they specified that they wanted the heat in kilojoules. They want the units on the delta H to be kilojoules per mole of HCl. All right, so I have negative 2,680 joules. How many kilojoules is that? Need to divide by 1,000. So it's negative 2.68 kilojoules. Okay, we reacted 50 milliliters of 1 molar HCl. So like our last unit exam, if I know the volume of the HCl and the molarity, I should be able to figure out the moles of it. How? We multiply the molarity of the solution by the volume in liters. Okay, so 50 milliliters is 0.05 liters. Multiplying gives 0.050 moles of HCl. So the reaction, when I mix the two together, the number of moles of HCl that was in the vessel was 0.05 moles. The amount of heat released by that reaction was negative 2.68 kilojoules. So now it just simply is dividing the heat of the reaction by the specific mole substance we want, dividing that and rounding to 3 sig figs, I get negative 53.5 kilojoules per mole of HCl. All right, so whenever we have a reaction that occurs in water, we are going to measure the temperature change of the surroundings. We're then going to use MC delta T to calculate the Q of the surroundings, the Q of the solution. The solute and solvent heat up the same, so we typically use the specific heat of water. Once we know the heat of the solution, the heat of the reaction is equal but opposite that, and then dividing by the moles of the reactant will give me the enthalpy of the reaction. Because when I divide this, it's going to give me a quantity of heat per 1 mole of HCl. Negative 2.68 kilojoules is released when we react 0.05 moles. Dividing that gives me the amount of heat released per 1 mole of HCl. And that's the purpose of the division. All right, let's turn the page. All right, now I have a problem very similar to the one that we just did. So I'm going to pause the lecture now. I'd like you to go ahead and try to do this problem and see what you get for an answer. When next time you click onto it, you're going to see the full worked out problem in detail that I'll quickly go over with you. But this is just a way to kind of save time and space. All right? So go ahead and do the problem. I'm going to pause now and complete the own work. And when you click back to it, you'll see the answers. All right, so here's the worked out problem for you. Hopefully you had a chance to do it yourself. The first thing you have to do is just like the last problem is figure out the heat of the solution. Now a common mistake that students do is they only want to put in 50 grams, but the solution is the entire thing. Not only does the water absorb heat when the reaction occurs, but also the ammonium nitrate particles also absorb heat as they chemically react and dissociate. And therefore, the entire solution must always be the total mass of the solution, both the solute and the solvent together, or all of the chemical reactants mixed in together. So the total mass of the solution is 51 grams. Again, we use usually the specific heat of water if they're water-based reactions. And then the temperature change. Now in this one, the temperature has gone down. So we get a negative temperature change. So the solution has got a negative value, okay? So therefore, the heat of the reaction is a positive 358 joules. Okay, to get the enthalpy of the reaction, we then have to divide the heat of the reaction, the Q value, because again, enthalpy is Q divided by N. We divide the heat by the number of moles reacted. That will then give me a value in heat per 1 mole of material. Well, the solute was ammonium nitrate. So up above, I took 1 gram ammonium nitrate. Now, since I knew the mass of the ammonium nitrate, I don't have to worry about using the molarity equation. It's a dry mass material, so I can figure out the moles by using molar mass. So very simply, divide the mass by the molar mass gives me the moles of ammonium nitrate. The heat of the reaction divided by the moles of ammonium nitrate give me 28,700 joules per mole of ammonium nitrate. That's how much heat is absorbed per mole of ammonium nitrate that dissolves in water. Okay? The value on the enthalpy is positive for this reaction. Therefore, is the reaction endothermic or exothermic? Not the solution, but the reaction. And hopefully you said endothermic, which is correct. An endothermic reaction is going to cause the water temperature to go down because it's absorbing energy for the reaction to occur, which is going to cause the water, the solution, to get colder. Exothermic reactions will release heat and cause the water, the surroundings, to gain energy and to become hotter. Okay? So again, always remember that it's opposite the sign. The solution will always be equal and opposite to the chemical reaction. One last thing to wrap up is this idea or concept of potential energy diagrams, which I'm going to get introduced to you today. We'll hit about it throughout the rest of this week, and more importantly, at the very end of this second quarter, we'll be doing something called kinetics. Potential energy diagrams is very important. A potential energy diagram shows the initial energy of the reactants. So this is the energy content of the reactants. This kind of shows how the reaction occurs, its pathway to get from reactants to products. Where it ends off is the energy content of the products. Now, in all potential energy diagrams, there is a little bump up, which is this B, from where the reactant started to this peak of the hill. This B section, this little bump up, is called the energy of activation. Most chemical reactions do not occur at room temperature because there's not enough energy to get them going. So, for example, if I wanted to light a candle, it just doesn't naturally just all of a sudden start to combust. Usually I have to add energy to it, which is usually from maybe a lighter, to give enough energy that now the candle begins to burn. So that's an example of energy of activation. It takes a little bit of a kickstart, some domino has to fall. Usually energy has to be supplied in some form, and then once the reaction gets started, then it continues just like the burning candle flame. Keeps on burning until all of it is consumed. So that's called energy of activation. If the products, the energy of the products is lower than the energy of the reactants, okay, the difference in height of A to D, okay, that difference in height of A to D right here, this is the enthalpy of the reaction. So if the products end up being lower than the reactants with their amount of energy, is this an endothermic reaction or exothermic? Has energy come in or is energy being released? And hopefully most of you said exothermic. And energy is going to be released, and therefore enthalpy should have a negative value on it. Well, C, value of C is the enthalpy of the reaction. Since the energy of the products is less than the reactants, there's a drop in energy, and that drop in energy has to be released into the surroundings because this is an exothermic process. The energy content of the products is not nearly as high as the reactants, and that extra energy has to be liberated out, and the surroundings will then absorb that release of energy. So A in this diagram stands for the energy content of the reactants. D is the energy content of the products. The energy of the reactants to the top of the peak is called the activation energy. And the distance from A to D, letter C in this example, gives me the enthalpy of the reaction. Key concept, if the products are lower than the reactants, this is an example of an exothermic reaction. Heat will be released by the reaction, and therefore the surroundings will get hotter because they'll absorb the energy that is released by the chemical reaction. Vice versa, we can flip this around. If the products are higher than the reactants, now the enthalpy again is still from the reactants to the products. Where do we start? Where do we leave off? Final minus initial. And in this case, we get a positive value, and this would be the enthalpy of the reaction. Now, they've actually given us energy values here off on the side, so we can actually assign numbers to this. So what is the exact enthalpy of this reaction? Positive what? Hopefully you said positive 50 kilojoules per mole, because we end at 100, but we started at 50. 100 minus 50 gives me 50 kilojoules per mole positive. This is an example of an endothermic relationship. So whenever you have an endothermic relationship, the energy content of the products will be higher than the energy contents of the reactants. What is the energy content of the reactants? Hopefully you said 50 kilojoules per mole. Per mole of reactant R, there are 50 kilojoules of energy. P, what is the energy content of the products? 100 kilojoules per mole. The products have a total summation of energy of 100 kilojoules per mole. Okay? The difference in those will always be the enthalpy of the reaction. Lastly, what is the activation energy? How much activation energy is needed for this reaction to occur? Well, the peak is at 250, but it started at 50, so subtracting, we get positive 200 kilojoules per mole. So it takes an energy of activation of around 200 kilojoules per mole for there be enough energy supplied to cause the reactants to form products. Okay? The higher the activation energy is, the more unlikely that reaction will occur. And if it does, it'll go very slow because of the amount of energy needed to cause that chemical reaction to occur. If it's exothermic, like the first graph, those reactions tend to be self-sufficient. The amount of energy released by the reaction is used to propel the further reactants to continue to react. And exothermic reactions tend to go to completion. Endothermic reactions, if you don't keep pumping energy into them, they typically stop or cease to occur because there just isn't enough energy to keep the products forming. Okay? So, big thing here is be able to identify potential energy diagrams. If it's endothermic or exothermic, again, are the products above or below the reactants? And those are key concepts to take away because you're definitely going to see more potential energy diagrams as we progress throughout this unit. Again, thanks for listening.